Hour of the long week. So we're going to figure out about NOx here. And if we have time, we'll do some about reduced chemistry too. All right, so in the atmosphere, there's some really important reactions you should know about. We emit NO from all of our combustion devices. And in the atmosphere, there's a lot of processes to make a radical HO2, the same radical we talked about before. And the NO reacts with the HO2 and makes it into OH. OH is really reactive, so even at room temperature in the atmosphere, it's reactive enough that it can react with a lot of stuff. And it reacts with all of the hydrocarbons there, either from human emitted or naturally present. And then the co-product is NO2. This is the brown stuff that makes the brown haze that you see sometimes in over smoggy cities. And it's colored, so it absorbs light very well. And when it absorbs a photon, it can break to make NO plus an O atom. And the O atom does a bunch of reactions that go back to make, for example, HO2. And the OH that's formed in this photochemical cycle, you can see that the NO, NO2 just go back and forth, NO, NO2, NO, NO2. It's like a catalyst. And the OH that's being formed each time will drive the oxidation of the hydrocarbons in the atmosphere. Some of those oxidized hydrocarbons react with oxygen and eventually become very heavily oxidized organics and super polar and high molecular weight because the oxygen's heavy and they're more polar. When you start with a hydrocarbon, you add more O's. And eventually it'll condense as like a liquid droplet or even a solid. And this is the way that the secondary organic aerosols form. And so that makes a lot of particulates, which is very bad for human health. And the whole oxidation rate is proportional to the amount of, they call it NOx, which is the sum of the NO plus the NO2. And another co-product you get from this, the O atoms can react with O2 and make ozone. Ozone is also toxic and particularly bad for people who have sensitive lungs, like asthmatics. So that's, in the United States, different regions of the country are rated by whether they are ozone non-attainment regions. That means that they're a place where the ozone level from the smog is so high that the government's decided it's dangerous to human health. And if you're in one of those regions, they have special regulations about the fuels and about cars and all kinds of stuff because they're trying to drop the ozone level down low enough that it's not going to harm people's health. Other parts of the country don't have this problem, and they're allowed to use whatever fuels they want in those parts. The NOx affects combustion chemistry also in several ways. So it's important in the atmosphere for sure. It also affects the combustion chemistry, but I would say that exactly what's going on is really not clear. There's a bunch of papers about this trying to figure out what all the NOx reactions are in the combustion. Empirically, it's known if you recirculate the exhaust, you bring NOx back in, you get some changes in how like an engine operates. And so it definitely matters, but it's not like gigantic effect. What's more important in combustion is that combustion is making the NO, which is polluting the atmosphere. And what's happening is you're starting primarily with nitrogen that's in the air, and you're reacting it to make NO. And that's the main source of NOx. And we'll talk more about that one. And then there's a bunch of different ideas about how to reduce the NOx coming out of the combustor to try to get rid of NOx coming out of the tailpipe. And so particularly for gasoline cars, we use a three-way catalyst. And that's a catalytic method for converting NOx back into nitrogen. And that way you just release the nitrogen atoms as nitrogen, which is innocuous. All right, there's several different mechanisms by which NOx can be formed. So there's a mechanism called the prompt mechanism, or sometimes called the Fenimore mechanism. It was proposed by Fenimore in 1970 and saw that right in the very primary reaction zone of the flame, you already had some NO, and thought that there must be some hydrocarbon radical that was reacting with N2 to explain that observation. And he suggested that this was the reaction, CH plus N2 to HCN plus N. We'll discuss this more and find that he was not quite right, but sort of halfway right. Another possibility is if you have some nitrogen in your fuel, then that nitrogen typically exists as a single N atom, and it's easy for it to end up as NO when you burn the fuel. And so that's a well-known thing. But you don't have that much N in most of our fuels. So this is kind of a relatively minor channel. This N can also form HCN. HCN is a toxic gas. It's cyanide. And so that's also pretty undesirable to emit. The HCN, if you have it inside the combustor, it can get converted into NO. And there's a paper by Miller and Bowman, 1989, that gives the mechanism for how the HCN can burn to make NO. A guy I used to work with, Tony Dean, discovered another pathway. He said if you have H atoms present in the presence of nitrogen, so in air, you always have a lot of nitrogen, H atoms can stick to the nitrogen and make this very unstable species called NNH. And the NNH mostly goes back to H plus N2, but there's some amount of NNH that's like in equilibrium with the H plus N2. And that little tiny bit of NNH, if it happens to hit an O atom, the O atom will add at this side and then split the NN bond and make NH plus NO. And this is a way you can make NO. And it's pretty hard to avoid because if you have combustion, you almost always have H atoms, and you almost always have O atoms, and you always have nitrogen if you're using air. So basically this is going to happen all the time, but it's kind of minor. So it wasn't even detected until like 1990s or 2000, something like that. So it's not the main source of NO, but it's a source. This one is the main source. It's called thermal NOx, or sometimes called the Zeldovich mechanism. And you have O atoms directly attack the N2, and they make NO plus N. And then later the N will react with either oxygen or OH and make NO. And this reaction, you always have O atoms, you always have N2, so it always can happen. However, this is super endothermic reaction. It's way uphill because nitrogen's really stable, and these guys are not that stable. And so this only is really important at very high temperatures. And that's why it's called thermal. It's like only when you get really hot do you burn air. Basically, nitrogen does not want to burn. So this is a very bizarre thing to burn nitrogen. All right. Here's a quiz for you guys. We have the thermal Zeldovich NOx production, O plus N2 to N plus NO. It's extremely endothermic, has a gigantic EA, very sensitive to temperature. In many practical combustion situations, like gasoline engines or diffusion flames, we have a stoichiometric mixture in the flame front, and that'll have the maximum possible adiabatic flame temperature. So we have just perfect match of the fuel and the air to reach the very possible highest temperature that you could possibly have. Right? There's no excess fuel, for example, or excess fuel to dilute to add extra heat capacity. So you just get the maximum temperature you can get. So what can you do in these systems to try to reduce the peak temperature? And then if you reduce the temperature, that's going to really slow down this reaction because it's super sensitive to temperature. So what could you do while keeping the stoichiometric fuel to oxygen ratio? Any ideas?
Species or residence time?
Okay, so one idea is you still have the high temperature, but somehow make the residence time at that high temperature lower. I'm not sure how to do it, but that's a good idea. Another one?
You could add a diluent to like spread out the final energy.
So you can add a diluent. So that's right. So you can have the fuel in the air in the right ratio, but have some third thing present and have that guy add extra heat capacity, and therefore the peak temperature will be lower. That's a good idea. Yeah?
Recirculating the exhaust gas.
Say again?
Recirculating the exhaust gas.
Okay, so that would be one way to do that, right? So if you take the exhaust gas, that could be like a diluent. So if you kept some of the exhaust gas and mixed it up with the fuel in the air, then you would make the temperature lower. Yeah?
There are some low temperature combustion concepts like HGCI and RCCI to like avoid hot spots in combustion chamber.
Okay, and so how do they get the temperature to be lower?
So the fuel is more evenly spread out for HGCI compared to regular diesel operation, and then you avoid hot spots or high Gs in the combustion.
Okay, so I think, so he was saying you can use HCCI or other kinds of low temperature combustion concepts. I think that those ones have two variants. One variant is you do mix with a diluent, and that will make the temperature go down. Another idea is you run very lean, fuel lean. So you have very little fuel, a lot of air, and then the extra air is acting as a diluent. That second one won't keep my stoichiometric condition, but the first one, if you can recirculate something or put something in there to dilute it, that's definitely can make the temperature lower and definitely works. It's a good way. So all these are really good ideas. And all of them, people practice it to try to keep the peak temperature as low as possible and the region of high peak temperature as small as possible, which is sort of the same as saying that the residence time at the high temperature is low as possible. Yeah, Andy, do you have something? Or no? Good. Okay. Let's go. All right, so this is the mechanism for the prompt and fuel nitrogen formation of NO. And this is from a very nice paper by Miller and Bowman, 1989, very important paper if you're working in this area. And basically say, like, if I can make HCN any way, HCN will react with the O atoms and make NCO, and then the NCO will react with H atoms, and the H will react with the N and make it NH plus CO, and then the NH will eventually go to N, and the N will react with NO and make N2. And so this is like a way you can burn it up. But the N could also react with OH or O2 and make NO, and that would be bad. We want that. We want that. Okay, and so this is like the channels, and these competitions of what the N will do, for example, is really important for making it how much NO we're going to make. All right? And in this paper, it gives the mechanism, has the estimates, the rate coefficients, lots of stuff. One of the reactions they think is important is if you have fuel nitrogen, it can go to HCN, or if you have hydrocarbon radicals, in particular CH, reacting with N2. This is what Fenn and Moore suggested might be the cause of the prompt low temperature and NO. So Fenn and Moore were saying, well, maybe it goes this way and goes down there. All right. And so people then tried to measure the reaction of CH with N2. And this is a compilation by Bouch of different measurements and estimates of that reaction. And you can see we have numbers. And you can see the temperatures are being measured, super high temperatures, 3,000 Kelvin, 5,000 Kelvin, really high temperatures. And then they get pretty high rate constants there, too. And part of it was that in order, well, if you want to see this reaction running, nitrogen is not reactive. So you need a pretty high temperature to see it really running fast. So a lot of people believe this, that the CH plus N2 reacted to make HCN, just as was recommended by Miller and Bowman. See, they had CH plus N2 going to HCN. But then in 2000, Moskaleva and Lin suggested that was incorrect. They said, if I start with CH plus N2, I can go to HCNN, but there's no way for this to go to HCN because I can't really spit out the N atom. And part of it was that it has the wrong spin state. N atoms are quartets. They have a lot of unpaired electrons, but this thing doesn't have so many. So it's spin forbidden. So they think that HCNN is not the root. Instead, they say maybe they go over a barrier that the CH comes in and it kind of grabs onto the middle of the two nitrogens and kind of makes a triangle. And the triangle widens out and then gets a little distorted where the one nitrogen comes up to the H and ends up making HNCN. And then that kicks out an H and makes NCN, a very weird species, plus an H atom. And this one is a total of 21 kcals per mole uphill, which is pretty endothermic, but not completely outrageous at combustion temperatures. So that's what they said, that's actually what's happening, that the major product is NCN, not HCN. So they said Miller and Bowman were wrong. This is actually what's happening. And so then some other people tried to test if that was actually true. So this is experiments done in shock tubes. They made CH a couple different ways, and then they added N2, and they detected CH, it absorbs at 431 nanometers, and they looked for NCN at 329 nanometers, and they saw it. And they measured the rate coefficient, and they found out that the branching ratio was 1. That means the only product they could see was NCN. They didn't see any HCN. And then people detected it also in flames. So if they had the right spectroscopy, they could see, oh, actually there's a whole lot of NCN and NH being formed there. And so this is all relevant to how do we get rid of NO. So back in 1975, so even before all this happened, a guy named Dick Lyon at Exxon found that if you added ammonia to something with NO in it, some of the NO and ammonia would react together and make nitrogen. And the overall reaction stoichiometrically would be 4 NOs plus 4 ammonias plus oxygen to go to 4 nitrogens plus 6 waters. And empirically, they varied the temperature, and they found in this temperature range, 11 to 1400 Kelvin, this reaction ran pretty fast. And if you add some more fuel, you can run it at even lower temperature, and it runs. Of course, the reaction does not run as written here. This is just the overall process. There's actually a whole bunch of microscopic steps that make this work. And the key is the reaction of the NH2 radical with NO. And that has the right stoichiometry to go directly to N2 plus water. It could also make NNH plus OH. Fang did a quantum calculation, and you can see the NH2 plus NO come together and make NH2NO, and then that isomerizes to HNNOH, and that isomerizes to another version of HNNOH, and then eventually these all go to yet another version of HNNOH because it's a cis and trans kind of molecule. And then you can finally go over a low barrier to nitrogen plus water. And so this is like the desired pathway to come this way. And you don't have to go over these high barriers at all. And this turns out to be the key reaction for the Dick Lyons process. And this is actually used commercially in smokestacks. So people squirt little bits of ammonia into smokestacks, and they reduce the NO coming out. And it works to some extent. The people went and tried to measure it, and so these are just several different groups, measured the branching fraction of how much of the NH2 plus NO went to the desired product N2. And then this is the rates, the K, as a function of temperature. And so you're in the region around here is the region of the SNCR process, and the rate's doesn't vary that much. So you have just basically a constant rate. And that makes sense because it's like a radical-radical recombination, so it doesn't have a barrier. So it's pretty weak T dependence. So this whole idea led to development of low NOx burners based on reburn. So the idea was, okay, let's first burn a bunch of our fuel-rich, not enough oxygen. In that region, we're going to make some NO, but because it's fuel-rich, we're diluting the mixture with extra fuel. It adds extra heat capacity, and also the fuel might pyrolyze, and the pyrolytic reactions absorb some heat too, because they're endothermic. And so we can overall lower the temperature, so we won't make as much NO. So that's the first idea. Then add some more fuel, and the fuel will do the reduction process to reduce some of the NO. And then finally, we have to burn up the rest of the mixture to burn up all the fuel, so we squirt some more air in. So that's the idea. This is used all the time now in many commercial burners to try to reduce the NO emissions. So even like a coal power plant, they'll squirt the coal in, and they have it set up with a system where they burn it rich and then lean and then rich and lean, and they try to keep the overall temperature not too high and give plenty of chances for the NO to get reduced back to nitrogen. And they found in this kind of system that this reaction is super important, that the NO reacts with this intermediate from the fuel combustion, and it makes HCNO and HCN, and then these guys do some other reactions that they had already characterized by the Miller-Bowman paper. Okay, so why is this all relevant to you guys? It's that we're going to change the fuels, and we're going to need new chemical models, and we're probably going to need new combustors. And so, we think that the fuels from biomass are going to power the airplanes. And the chemical engineers will try their best to convert the biomass into jet fuel, but it won't be the same. And so there's going to be some new kind of jet fuels coming. Currently, we call these things SAF. As it gets to be more gigantic scale, where they try to replace more and more of the petroleum and make the jet fuel more and more from biomass, they're going to have to use a lot of biomass. And they're going to have to figure out some process that works on gigantic scale. And who knows exactly what the fuel is going to be after they do all that. And I think likely there'll be several iterations of what the fuel is, and maybe do fine-tuning of the engines to try to adapt, because they really won't want to spend the amount of money it would take to make the biomass into exactly the same as the petroleum jet fuel. And they'll have to check what works well in the airplanes and everything. So this is a one big line of research that's sort of started, but it's going to be big for at least the next 10 years, maybe 20 years, as they try to figure out how to basically get rid of all the petroleum and jet fuel. Another idea that people think is going to be big is burning ammonia, or maybe mixtures of ammonia and hydrogen. And this would be a zero carbon fuel, so you have no CO2 emissions if you go this way. You don't need any biomass, so that's actually a big advantage when you're on big scale. In Japan, the Japanese government is really excited about this idea, and they're subsidizing people to import ammonia and burn it and figure out all the burners and everything. This is a totally different story from hydrocarbons. There is no carbon, there's no CO, all the stuff we're used to is not there. It's all new molecules. They have their own weird behavior. Their flame speed is 0, very small. So it's really difficult to burn it. And you get gigantic NOx emissions, and maybe sometimes some NO2O emissions as well. And so then you really have to work a lot on emission controls to make this work. So people are really excited about it. Possibly this is the future. I have some grants from an industrial sponsor who thinks it's the future. I don't know if it is, but for sure if it is, working out how to control the NOx emissions is going to be a gigantic issue. And how to do it very reliably, because the amount of NOx you make is at least an order of magnitude, maybe 2 orders of magnitude higher than what you would get from burning hydrocarbons. So it's quite a lot of NOx, and so you need to have really, really, really good emission controls to make this work. You can change it some by how you operate the combustors too, and so that's also definitely a topic of great interest. All right, so that's the end of that one. Questions about fuels, NOx? All right. Grand finale, numerics. Probably you guys like this stuff anyway, more than chemistry, but it just shows your bad taste. All right. So these slides are mostly from Professor Tianfeng Liu. His life is figuring out how to do mechanism reduction, how to take complicated chemistry models and make them small enough that they'll work inside computational fluid dynamics simulations. He works a lot with Dr. Chen, Jacqueline Chen, who gave the talk about the really big CFD simulations and DNS, because her computer definitely cannot handle some of the mechanisms that my group would make. So just a reminder, you need detailed kinetics. Even the simplest fuel is not simple. And you need realistic chemistry for every fuel and every reaction condition. And just because you have a model that works in one temperature range does not mean your model is going to work at another temperature range. So, for example, this is ignition delays. You can have models that work great for high temperature ignition delays, but if you extrapolate down to lower temperatures, you'll be completely off by orders of magnitude off in the ignition delays. And so you have to put different reactions become important in different regimes, and you have to make sure your model has them. You can get quite complicated behaviors. Like this is what happens with methyl decanoate when you put it into a perfectly stirred reactor. You get this very weird double back thing where you have like multiple branches, and you can have different stable operating points, depending on your history. Like you have hysteresis and how you operate the thing. If it started at high temperature, you lower it down, you can keep it stable for a while, then something it'll extinguish. So you come down, it'll extinguish. Then when you go back up, you'll get to some completely different regime and jump up to here maybe. So very strange. And this is all because of the very complicated chemistry. And the chemistry models are huge. So for transportation fuels, typically we need about 1,000 species, maybe 10,000 reactions to accurately represent the fuel. And you try to do simulations with a detailed chemistry, this gets to be really expensive. 1D is fine, but when you get to 2D and especially 3D, this is really, really hard to do. And you get a lot of output data. If you run with a CFD simulation with 1,000 species, it means you have 1,000 state variables at every finite volume. If you have maybe a million mesh points, then you have 1,000,000 times 1,000, so you have like 10 to the 9th numbers that you're computing at every time step. So this is kind of bad. Just to store the output, if you run 10,000 time steps times 10 to the 9th, you have like 10 to the 13th numbers that your computer is spewing out at you. And what are you going to do with 10 to the 13th numbers? So this is a real issue. The reaction rates are determined by the temperature and the species concentrations. It's pretty local reaction states. And you can have different, in the CFD simulation, you can have completely different things happening in different finite volumes. And you can see that in a real burner. You can see like, I have a flame here, it's doing a lot of chemistry. Up here, I just have exhaust, not doing much. Down here, I might have cold fuel and air, it's not doing much either. And so like, obviously the chemistry is like wildly different in different locations. And different reaction pathways are controlling at the different conditions. So you have a model that works well at one reaction condition, can be wrong at other ones. And then any mechanism reduction is going to be specific to the particular reaction conditions you're trying to match. You want the model to work at some conditions, but there's no way a reduced model is going to work at every condition. You have to figure out about that. You can't figure this out unless you have some idea what the concentrations are. For example, like the fuel rich is really different than fuel lean. So you have to know before you start, in my CFD simulation, am I ever going to have a fuel rich region? If I am, then I have to make sure I put some fuel rich chemistry in. If I can ensure that I'm never going to have fuel rich, then I don't have to bother. And that will save me a lot of headaches. I don't need a soot model. I don't need to worry about all kinds of pyrolysis stuff because everything's just going to react with oxygen. You can try to do what's called reaction state sampling. So if you have a reactor or a preliminary CFD simulation, you can use that to get estimates what the temperatures and compositions are in different locations. And then that can help you to identify what chemistry you need. And then you could take that chemistry and put it back in and run again, and you get a slightly different solution. And it'll tell you more precisely exactly what chemistry you need. And you could iterate this a few times to try to really narrow in on which chemistry models do I need that hit the conditions that are actually encountered in my device that I'm trying to simulate. And so Professor Liu often does some reactors that simulate autoignition, some do perfectly stirred reactors, some 1D laminar flames, sometimes turbulent flames, and from these extracts a bunch of reaction conditions that he needs his model to work at because he knows he's going to hit these conditions. And so this shows how he does the sampling. He'll run a bunch of different temperatures, a bunch of different feeds, different pressures. It can run, see how much of the H atoms he's forming at each different case. He knows he only needs high H atoms at high temperatures, so there's correlations between the variables. that in the place where the high temperature is, you need all the high temperature species, but you don't need the fuel, because the fuel won't be left anymore by the time you get to high temperature. You can do sampling from the perfectly stirred reactor, and you can see like all the conditions you get for different resonance times and different temperatures in the reactor. And you can say, well, I'm probably going to have a lot of well-mixed cases in my real device, so I better sample those conditions. Now, when we write down the equations, we have the transport equation, which has to equal the chemistry term plus a bunch of transport terms. And this chemistry term is the question. It's like, how detailed does this have to be? And then typically, what we'll do is we'll discretize in space. We'll have like a spatial mesh. And then we're actually going to do the time derivatives by time steps. So we're going to have finite time steps. And so we're discretizing both kind of in time and in space, but kind of separately from each other. But they're related to each other by the CFL number. So if you do a certain meshing, you have like a certain, you have to keep the delta T commensurate with the delta X by the CFL condition to make it stable. So suppose we have a time integration of the stiff differential reacting system. We have a convection term, we have a diffusion term, and we have a reaction term. And this y vector includes all these variables, the temperature, the species, concentrations, all the grid points. And so you can't typically solve this because the dimension of y is too large. As I said, it's the number of species times the number of mesh points. And that's really too large for a stiff solver, because the stiff solvers have to construct the Jacobian of that thing. It's too big. It won't fit in the memory of the computer. So instead, you either have to go and use fully explicit solvers, so you don't need a Jacobian, and that can work. And then you can just pick the small time steps to correspond to the convective and diffusive timescales and solve it. But because the species timescales can be really tiny for very reactive species, like OH, for example, might only have a reactive timescale that's nanoseconds. And so then it's like super difficult to solve explicitly because you'd have to use such a tiny little delta T. So more commonly, you can't do it that way. And instead, you need to do stiff solvers. So to do stiff solvers, we'll separate the chemical terms from the transport terms and then do Strang's splitting scheme or similar splitting schemes. And this is how it works, is you solve the chemistry terms for half of a time step, then you solve the transport terms for a full time step, then you solve the chemistry terms again for another half a time step, and it turns out at this point you actually get a good approximation of what you would have gotten if you would solve the whole thing together for a full time step. And this is due to Gil Strang's brilliance that he figured out that this would actually work, and he proved the error bounds and how big the error is. The transport is linear and has a highly structured Jacobian and only very weak coupling between the species, and you can use special solvers. So this step, the transport step, is not usually so difficult, though if you have more than 1 million mesh points, it still might be pretty difficult. But that's one step. The chemistry is highly nonlinear, is stiff, and you typically have to solve it implicitly. But the chemistry terms are local, so you can solve each mesh volumes independently of the others. And in particular, you can do it in parallel. And so this is the trick that the CFD people use, is that they can take these solves, which are the expensive ones, because they're implicit. They can solve them on a gigantic, massively parallel computer, and each core is like solving a different chemistry solvent at the same time. And so if you have 1 million mesh points, but you have 1 million cores, then you can just distribute over all of the computer and use it all to solve them all at once. And so that turns out to be hugely beneficial. However, the splitting schemes introduce a different numerical error and sometimes a new numerical instability. So we're making a different approximation. When we solve this together compared to solving this scheme, it's not exactly the same, and you get extra errors. And so therefore, then people invented a bunch of different splitting schemes that are slightly different than the Strang one to try to avoid problems they saw with the Strang splitting. And each of the different splitting schemes has its different pros and cons of accuracy versus stability, numerically, and also cost. And if you're interested in this topic, you might want to read a paper by Speth in 2013 that has shows several different splitting schemes, and then what happens to the errors, and which ones are best for which situation, and the numerical instabilities. The Strang method has pretty good stability properties, and so that's really very favorable aspect of the Strang's one. And so I would say this is the most popular, but people have proposed a lot of other ones because this is still not great. You're trying to solve these differential equations. If they're stiff, you have to solve them implicitly. So you say, well, dy dt is approximately the change in y divided by the change in t. H is just delta t. And you can rearrange this to get an algebraic equation that relates the new y well, it gives an equation for the new y. And you can see that the new y appears inside this function g. And so that's why we call it an implicit method, because we don't have an explicit equation for y, the updated y. We have it inside another function. So we have to solve this typically nonlinear function by like Newton's method or something like that. And so that's what this is. We have to construct a Jacobian just like you would normally do for Newton's method to solve it. So there's the Jacobian, you solve it by Newton's method. And this is, you have to solve iteratively several times to get up to the new value. So you have to evaluate the source terms, you have to evaluate the Jacobian, then you have to solve these linear equations by factorizing this large Jacobian, and then solve the linear equations. You have to do it multiple times. So this is why it's so expensive. The amount of time it takes for the chemistry is typically something like 5 times the number of species squared. So as the number of species gets large, this gets to be pretty expensive. But diffusion is actually not that much different. So if you do mixture average, you have to do about k squared. If you do more exact treatments of diffusion, multi-species diffusion, it's even more expensive. So they're a similar cost. If you could reduce the number of species, that would help you a lot. This would get cheaper, this would get cheaper, your memory would get smaller, your output would be smaller, everything would be better. So you'd really love to make the number of species smaller. So let's see what we just go down. Actually, before you do that, one idea is just try to evaluate the Jacobian better. And a really nice thing you can do is you can make the Jacobian really sparse, and then the amount of memory you need for the Jacobian is less, and also the cost of constructing it is less if you know that some of the elements are 0, and also the linear solves are cheaper. And so it turns out with clever choice of how you formulate the equations, you can try to make the Jacobian really, really sparse. And so, for example, here's the one for the LLNXL model for heptane, 561 species, but you can see lots of swaths of zeros. And so that's pretty good. And you can even do better than this one, actually. So you have all these choices. You have explicit solvers, but you only can do it if the model's not stiff, and typically this is not possible or not that often. Or you have implicit solvers, and then you have to worry about all these steps. In principle, the LU factorization scales as the number of species cubed, so your scaling could be really bad. But in practice, this step is actually cheaper than this step of constructing the Jacobian, so usually you don't get to this limit. And if you can make them sparse, then everything can become first order in the number of species, which will be great. All right, so now I said we have too many species. It would save us memory. It would save us CPU time if we could reduce the number of species. And we have a lot of ideas about this. One is like you just say, I hate this species. I'm going to cross it out. Okay, so that's the idea of skeletal reduction. Or you say, I hate this reaction. I cross it out. And we really want to cross out species because that's going to reduce the size of the Jacobian and the size of the memory. So we just basically want to pick out some species that we decide are too boring. Who cares? Cross them out. We want to cross out like a lot of them because we're trying to get reductions of like, factor 10 or something. Cross out lots and lots of species. Now, how do you decide which species you can fairly cross out without screwing up your accuracy? And so what you can do is if you have the full model, and then you propose a model where you've crossed out a lot of species, you can actually compare the predictions. And in particular, you can compare what the omega value is. So you have the omega you have for the full model, you have the omega you have for the model where you cross species out. And if you see any really big discrepancies, then you're worried, oh, that was a bad idea, I shouldn't have crossed that out. And so you can try to judge it that way. And in fact, you can do a math problem and prove like what the optimal species to cross out are. And if you have an error tolerance on omega, you can adjust it to try to make exactly whatever error you want. And so my student Olawole published a couple papers about that. So that's like one idea. But that's actually pretty expensive to do an optimization. There's a lot of possibilities of what you could cross out. If you have 1,000 species, there's like many, many combinatoric ways of which species you could cross out. So a better way to do it for speed is to do what's called the directed relation graph approach, DRG. And this was invented by Tianfeng Liu when he was a student. And this one can be done on the fly. So as you're solving it, you can just decide which species to ignore at this time step. And then keep doing that. And then later, if they become important, you can automatically leave them in. So you can kind of like on the fly decide, I'm not going to bother with that one this time. But then later, when it is important, I'll put it in. And it's all evaluated for you automatically. So this DRG thing is pretty great for speed. There's another version of this called DAC, Dynamic Adaptive Chemistry. Originally, I think, invented by Professor Zhu in this department. Then later, so there's a group in China that's been following up on that. And that's also sort of a same idea, but a little bit more fancy and better version of it. Another thing that you probably did as students is quasi-steady state approximation. You say, let's go look at the really transient species and say, well, those guys are going to be locked in algebraic relations with the major species. And so I can replace the differential equations for those guys with algebraic equations. And if I can solve the algebraic equations, for example, if they're linear, then this is really great. And so that's a popular method. There's a more like general mathematic version of this called CSP or ILDM, where you can there's a general math formula about this kind of idea, but kind of more generally. And this kind of math can work really well. Usually there's like broad ranges of conditions where you can make a certain reduction that's really accurate for a while. But then eventually the chemistry changes so much that you have to do something different. So you'll end up with like a manifold that for a certain region is like a simple smooth manifold you get, but then you might have to change the dimensionality of the manifold when you get to something funky happening, like an explosion. And so there's a whole literature here, and there's a bunch of groups that are like specialized in how to do this automatically. Another approach is say, well, I just assume that some reactions are so fast that I can assume that at time 0 they're all done. And that's the high chem approach, where I say, well, like the fuel has already fallen apart. Therefore, I don't need any fuel chemistry. I just need to know about what happens next. And that's in some situations that can be really good. And then there's a bunch of very numerical kinds of techniques like tabulation that if in some situations work really well. But each is it's sort of a complicated story. A key issue is that we usually don't know what the error is that we make when we do these model reductions. There's been several attempts to try to control the error, and in some really special cases, like Olawoi's case, you can derive error bounds, but most of the time you cannot. So most of the time we can reduce the model, but we don't know what error we introduce when we do that. And this is really bad. So you have like an uncontrolled approximation. And then by trial and error, you can like try to reduce it not quite so much and see if it changed or something like that. But this is also very similar to CFD. So often when people do CFD, they try it with some mesh. And then they say, hey, let's try some different mesh and just see if it's changed. And it's also not super scientific to like know if you really have the optimal mesh size, right? And it's the same thing in the chemistry. It's like, what's the optimal approximate chemistry to use? It's hard to figure it out. It might be possible, but usually it's like so much work to figure that out that people don't do it. And ideally, you want to like adaptively change the model reduction as we solve the reacting flow simulation to get automatic error control. And this is not done routinely today the DAC gets like an idea about how to do it, but I think this has not been practiced. And part of it is that the CFD calculations are so expensive that it's hard to do a lot of iterations with rerunning the CFD with different reduced models to check whether you really did it right or not. But I think as the computers are getting better and better, this should be more feasible to do. And there's a lot of different ideas about this. And so, for example, these papers have different ideas about how to decide whether it's better to adapt the model structure or maybe just decide which of the species are allowed to be changed in a certain time step. A lot of different ideas about how to do it. And this is like very active research area. Professor Liu has worked a lot on trying to make it possible to use the explicit solvers because they would be so much easier than the split stiff solvers. And the key then is you have to identify what is causing the stiffness in the model and what can you do. And so he invented a method called dynamic chemical stiffness removal that identifies right now what's causing the stiffness, figures out some approximation to remove it, and then integrates a little farther and then finds out something else is causing stiffness now and does some trick to remove that and keeps doing like that. And he's had a couple of good cases where he was able to do this successfully, and then they were able to put those non-stiff models into Professor Jackie Chen's simulations, and they actually worked to use with the explicit solver. Because originally the Jackie Chen's models all used explicit solvers. And if you can, they're really fast. But then later found like most of the time it's impossible. But at least for some cases, they were able to do it using this trick. And that's it. So you guys have now successfully completed how many hours of classwork in 1 week? Pretty good. Questions? All right, well, thank you very much and have a very nice, safe trip back. And I hope next week you still remember some of what you learned this week.